In this session, I'll be talking about the IEEE 30,000 foot level reporting for continuous data when the distribution is non-normal. At the end of this module, you'll be able to describe how to apply these 30,000 foot level techniques in the EPRS with the EPRS Minitab add-in for non-normal distribution where there's continuous data. In the overall decision tree for which particular tool to use when creating the stability chart for the 30,000 foot level report out, you would use this graphic on this page number 278. Then you would, now that could involve a transformation, and these are various Box-Cox transformation. Whenever Box-Cox is 0, that's equivalent of a log transformation, which we'll be focusing on that since it really has widespread available usage, applicability. Now this is called a power transformation. Minitab evaluates a series of transformation and which reports which power is the most normally distributed after taking the transformation. But it's really important to keep in mind that we need to use a transformation that makes physical sense. Minitab evaluates lambda values from -5 to 1, but I don't know what a lambda value of minus 4.73 is. So to me, you really want to go in and consider the ones on the right-hand side, because those would make some physical sense. For lambda Box-Cox transformation to work, you can have no negative numbers. Now sometimes if you have that, then you can do some shifting and so on to get around it. But again, I want to emphasize that transformations need to make physical sense. This is some other guideline for things that could make physical sense. I can't emphasize it enough, but you need to make a transformation that needs to make physical sense. Now, typically, whenever you're doing the subgrouping, and you don't need to do one for the mean value because of the central limit there, but for other situations that you will need to take that, for example, even though that the mean value is stable and the log of the standard deviation is stable, you're actually dealing with raw data when you deal with your capability assessment, and that data may need to be normally transformed or log normally transformed. So this is kind of the overall roadmap and that you would follow. Now, especially when there's a lower boundary, like it can't get below 0, like for example, lead time can't get below 0, well then that's a clue that log normal distribution may be appropriate transformation. So this is looking at the stability metric, and you notice again that there's situations or nomenclature there where you might need to take some transformations. So this is an example. You can pull up this data set, and then I suggest that you follow with me. Stop the video whenever it's appropriate to catch up and be able to follow along with me. So there's an upper spec that you like to have 0.02, but there's a natural lower boundary of 0. So if you plug the numbers in for IEEE no subgroups like that's shown here, then you get this plot here. Now you notice how on the individuals chart on the left-hand side, there's a natural boundary of 0, but it physically can't get below 0. You notice how on the right-hand side, the probability plot has a curve to it. That's another indication that a log normal transformation would be appropriate. I think I covered all this already. So to make the log normal transformation, you go into EPRS, IEEE no subgroups, and then under the dist option there, or the dist parameters, then you type in the word log normal. And you come out and get this plot here. Now notice we have 2 points that are beyond the upper control limit, so therefore it says the current process is not predictable. There still seems to be a little curve to it, and which may indicate that there's more than one distribution. But what we're going to do is consider that that's close enough. This is actual real data, so real data never performs as well as you might like it to be. I think it was Bach said, no model is perfect, but some are acceptable, and that's what I think we're looking at here. So what we can do, since they're kind of close control limits, we could ignore them. Now we do have rights to investigate and see if we can learn from seeing what might have happened there, but I'm going to go in and take out the limits, especially since it's close to limits. When you do that, you put the option NOOC of 0, and then it comes in and ignores those 2 points that are outside limits. So now it's talking about a nonconformance rate about 46%. It's kind of interesting, I think, that people get all wrapped up around the 2 points that are beyond the limits. But our real issue here is we got a 46% nonconformance rate. Now, in order to address that, we got to change the process. That's harder and takes more work or a different effort than looking at those 2 individual points. So again, if this level is unacceptable, and 46 sounds kind of high to me, then that measurement pulls for the creation of an improvement project. We already talked about that. There might be more than one distribution in this set of data. So, for example, the particular response that we get might occur differently because you might have sometimes you have 2 machines, or you got 2 different shifts, or something else that could cause that difference. Here's another situation looking at day sales outstanding. It's got a target value. So this is kind of how the data looks like relative to our target value. There's a natural boundary. So pull up this data set and follow along with me. So if we did this, then we get a plot that looks like this. Well, you notice now that it's got values below 0. It's also got a curvature to it. So log normal looks like it would fit, but fortunately it's got values below 0. So if we did a probability plot of that, and we did a 3-parameter log normal, what we notice is it's got a threshold value minus 29. So if we go in and put a shift of minus 30, you could put 29 in there, and you put that into that option, then what you can get is you got a 30,000 foot level chart where you're dealing with basically a 3-parameter log normal distribution, and you notice how it fits a curve real well. So whenever you do this, you're going to have a curvature on the probability plot, which is what you would expect for this kind of situation. But the points do follow the line quite well. So if we're removing the specifications as an add-in, we can then find that now we have the 80% of the values between this value here. So you can present the data in different forms. So the first one was dealing with estimated percentage nonconformance. Now you can report actually the mean instead of the median. So then you put UMN and put the add option 0. You plot it here. Now you can see it's got the mean value instead of the median. So I want to emphasize, if any of these 30,000 foot level charts are unsatisfactory, then that metric improvement pulls for an enhancement effort. Demonstration that an improvement actually occurred for this activity or process is when the 30,000 foot level individuals chart shifts to an enhanced level of performance. So in summary here, we learned how to use the EPRS Minitab add-in for easy creation of 30,000 foot level charting, and also how we can estimate capability at the same time, all in the same plot.